Assalamu alaikum. Welcome to this live stream. I am honored again to have Paul Nelson back at the channel, one of the legends of the intelligent design movement. Paul, this is going to be your final live session, and we're going to have a break for about a year. It's making me sad, but at the same time, it's making me happy because of some news we're going to be sharing at the end of this live stream.
Right. Um, One could say life is a zero-sum game, and time that I devote to, putting together these streams, I have to take away from other projects, and I really want to finish a very important project, so we can discuss that at the end.
Brilliant. Thank you. All right, over to you, Paul.
All right, great. So we've been trudging along a rather long road about the significance of orphan and taxonomically restricted genes. And in this concluding section, part 7, I want to pull together several threads from the previous 6 presentations, sort of tie them up together with a thesis. And we'll do it with 4 key lessons. The first is the least controversial. In fact, as we go through these lessons, they'll become more and more controversial until the last one, which will be the most controversial of all. But the least controversial is, number 1, genetic and proteomic space is vastly larger than anyone realized before 1995. The significance of that date is that in the mid-90s, 1995 in particular, the technology of whole genome DNA sequencing became a practical reality. And biology was able to gain a glimpse, which has continued to expand since the mid-90s, of the actual dimensions of genetic space on planet Earth. So a consequence of that is perhaps not obvious, but I hope to spell it out in the longest section of the presentation today, and that is point 2, or lesson 2. Evolution is not a theory of similarity. It is a theory of transformation. And the significance of this, I hope, will be obvious when we go through this part of the talk, particularly when we look at the number of orphan genes and proteins in the virosphere. That will take us to point 3, which is the origin of life and evolution, far from being separate questions, are as closely connected as any 2 puzzles can be in science. And then lastly, lesson 4, the origin of life represents the scientific crossing over point from evolution to design. And by evolution, I mean standard theory in which evolutionary change occurs via undirected physical process. And the most controversial point of all will be the closing, which is to make that crossing, to go over that bridge from evolution to design, one must let go of something. So we'll have a little philosophical epilogue or coda to these 4 lessons. All right, 1. Genetic and proteomic space is vastly larger than anyone realized before the mid-90s. So this technology, which now is increasingly rapid and inexpensive, did not exist when I was a student. And I have had the privilege of living through this revelation. Well, it is kind of a revelation. This revolution, which really has changed biology in ways that I think the science has yet fully to come to grips with. So I showed this figure in an earlier presentation, and it gives a graph representing the growth in sequence data in GenBank since 1990. Okay, and you'll notice that the vertical scale is logarithmic. So we have really an exploding universe of information about, the genetic basis of life life on planet Earth. And we have two lines here. One is the blue slope, which is the number of gene sequences. And then the red line are whole genome sequencing projects, where some species is sequenced in depth with respect to the DNA that it possesses. So the NCBI, when they provide this figure, point out that from 1982 to the present, the number of bases in GenBank has doubled approximately every 18 months. And it would be a great paper if someone would write the biological equivalent of Moore's law in transistors. A remarkable prediction made by Moore that has been followed really in a really striking way in the development of electronic technology. I would love to see the biological equivalent of that, this doubling of bases in GenBank, every 18 months. Now, what's happened quite recently is, given the advance in computational tools and modeling of sequence homology, it's now possible to take a global view of what is the signal that's emerging from all of this sequence data. So this paper, which I think is really first rate, by Bookfink et al., I'm not aware that it's been published yet, but you can get the preprint at bioRxiv. They looked at the trend lines in the accumulation of genetic data with respect to things like how do protein clusters track as more and more genomes have been sequenced. So this blue line that you see on this figure shows eukaryotic protein clusters, where the total count is on the vertical axis and the number of genetic assemblies is on the horizontal axis. And you can see that you've got a steady linear increase that's not coming down, as they call it, a monotonically increasing graph. And the moral that the moral that they take from this is that eukaryotic sequence diversity space is not fully saturated yet, meaning as more and more species have their DNA mapped and sequenced, we will continue to see an increase in protein clusters. On an analogy to natural language, this would be like writing the dictionary of English and finding that every year you would run across new words that you hadn't seen before. In fact, the OED, Oxford English Dictionary, publishes annual updates, but most of what's in those updates are not novel words in the sense of words that we haven't seen before. Most of what's there are new meanings assigned to existing character strings, existing words. But this would be, to stick with the analogy for a moment, this would be a case where entirely new character strings were being constantly discovered as more and more English texts were surveyed. So it's a remarkable pattern. Now, what's really remarkable is the Orphans fraction. So this curve here shows that most of the data that they examined falls into what they say is about 92% of the sequences. So this portion of the graph here are protein families. Then we have protein pairs. And then we have the singletons. Now, this is a very large number of unique sequences, almost 2 billion. And the significance of that is when you think about the definition of what orphans or taxonomically restricted genes are, it has, reflect on that number, almost 2 billion, has powerful implications for evolutionary theory, because these sequences in this region of the figure are by standard bioinformatic criteria at least equidistant from each other. That's implication one. Implication two is their possible functional roles. In other words, are they essential in terms of, let's say, some cell function or some organismal function, such as development? If they are essential, that may have consequences for the transformations that are required to occur from the last universal common ancestor to the present. So there are parallel implications here. Distance in sequence space, which I'll talk more about later on, and then functional roles, which I've already mentioned in previous streams. Both of those emerge directly from this very high number of unique sequences. Now, the way I think that is most effective for considering the significance of orphans is to look at them in the virosphere. So we find them in multicellular eukaryotes. We find them in unicellular eukaryotes, protists. They are abundant in bacteria and archaea, those two domains of life, but they are most abundant in viruses. So just to take an example of this, a French group looked at what are known as, or what they dubbed, Pandora viruses. These are very large viruses whose genomes are larger than many free-living bacteria. And what they found was quite remarkable. Again, as is the case with all my previous presentations, I will supply this reference to Subor, and he can attach it to the YouTube file so you can track these papers down for yourself. But they looked at the functional roles of the protein coding sequences in these Pandora viruses. And you can see along the horizontal axis here, we have different species of Pandora virus. And they've divided up the proteins into their functional roles. Now, what's remarkable is the gray bar, or the gray portion of the bar, which here is listed as unknown function. Why is that significant? Well, unknown function is significant because there is a direct connection in annotation between a function, or a missing function in this case, and orphan status. Not all proteins of unknown function are orphans, of course. But unknown function tells you that when the sequence is annotated and you compare that to what exists in genetic databases, if there were a known function, there would be a homolog or ortholog for that sequence. So the fact that you don't have a function to assign to something that looks very much like a functional protein tells you you may have an orphan. So look at how much in these bar charts is assigned unknown function. Big gray regions. Most, in fact, of the genomes of these Pandora viruses is unknown function. So in their paper, they say the dominant category by far is that of proteins lacking recognizable functional signatures. Across the 6 strains, so that's right here, these 6 groups, an average of 70% of the predicted proteins correspond to unknown functions. Such a high proportion is all the more remarkable as it applies to carefully validated gene sets from which dubious open reading frames have been eliminated. So they think they've got high quality data here, and they find it very striking that in these Pandora viruses, most of what's there doesn't have an assignable function, even though it looks to be functional. They go on. What characterizes the Pandora viridae is the unprecedented number of family-specific orphans they share. The increase of their proportion among the subsets of core genes, clade-specific and strain-specific genes, as well as their statistical properties. And they go on to say these Pandora-specific orphans are not, missing from the databases. Rather, they are specific to this group of viruses. Eugene Koonin is one of the, I would say, world's leaders in this area in terms of trying to characterize what's going on in the virosphere. And in a paper last year that I, again, recommend to you to track it down, he says, how many viruses do we have? What's the global virome? Well, he says we can estimate it crudely at 10 to 7 to 10 to the 9 distinct viral species. A huge number. Now, he says, obviously, we haven't sampled all of that. Currently, we have 10 to the 4 recognized species, but it's likely that the total number of viral species on the planet is somewhere between 10 to the 7 to 10 to the 9. Well, what's a consequence of that genetically? He says we can roughly estimate the size of the virus pangenome. That is, what is the total number of viral genes within all viruses considered globally. Total number of genes in the virosphere. He goes on, large viruses encompass many poorly conserved species-specific genes, another word for orphans, that obviously represent the bulk of the virus pangenome. So he says, assuming 10 such unique genes per virus species, there would be 10 to the 8 to 10 to the 10 unique virus genes altogether, a vast gene repertoire, to put it modestly. Now, again, when you see numbers like this, you need to keep in mind the definition of a virus. You need to keep in mind the definition of a virus. Yes, you need to keep in mind the definition of an orphan. An orphan is, by standard criteria in bioinformatics, as far away from other gene sequences as it's possible to be. So these are equidistant from each other in sequence space. All right, keep that in mind, and then now let's segue to the implications for evolution, which I am summarizing here as lesson 2. Evolution is not a theory of similarity, it is a theory of transformation. Okay, here's a little tree shrew, handsome creature. And let's say we observe this species longitudinally for many generations, and we see no change. All right, there's stasis. In fact, we go to the fossil record of these tree shrews, and their fossil form is identical to that of the extant species. Well, that's not evolution. Similarity without change is stasis, okay? Let's contrast that situation to this one. Now, I'm not arguing with this slide that tree shrews are ancestral to fruit bats. We don't know what the actual ancestor of fruit bats was. It was probably something like a tree shrew. So this guy is standing in for the unknown common ancestor of Chiroptera, Mega and Microchiroptera. If you go into the literature on mammalian evolution, it's argued that the ancestral form for the bats was something like a tree shrew. So with that caveat in mind, I just want you to recognize this is just a stand-in for the unknown common ancestor of the bats. All right, this, in contrast to the first case, this would be evolution, the transformation of A into B. So this may seem simplistic, but it's a very important thing to keep in mind, that evolution, in its essence, in its nature, is transformation over time. Okay, why is that relevant? Well, if you think about how you know that a transformation has occurred, you require some trace of similarity to show that it actually occurred, which is what we expect, let's say, from the fossil record, or what we expect from genetics. Why would a paleontologist say that something like a tree shrew was ancestral to the bats? Well, he's first going to look for a mammalian common ancestor. He's going to look for an ancestor that has the basic skeletal pattern of a mammalian, of the mammalian form, right? So he wants some signal of similarity in order to argue that there was a process of evolutionary transformation. Okay, now this creates a paradox. Namely, evolution as a theory requires some similarity, but not too much. Why? Because similarity at its theoretical maximum is identity. So Subor and I are having a conversation, and I'm assuming that there is one Subor in the United Kingdom, not two. In other words, if there were a person who were identical in every respect to Subor, that would be the theoretical maximum. So similarity taken to its theoretical maximum equals identity. And identity biologically is stasis. So Lingula, enigmatic fossil form that we find today, appears to be identical to fossil forms present hundreds of millions of years ago. There's been remarkable stasis in that group. Horseshoe crabs exhibit remarkable stasis. In other words, lack of change, lack of transformation. So no similarity between two or n entities gives us no historical signal of transformation. So too much similarity is a problem for evolutionary theory, and that, I think, is paradoxical. Too much similarity erases any signal of transformation. Let me go back because I misread this slide. No similarity between two forms, two entities, gives no historical signal of transformation. In other words, if they're totally different, you can't make a case that they are related by a process of transformation. All right, now, getting myself squared away, too much similarity also necessarily erases any signal of transformation. So let's follow up the implications of that. Remember, I argued stasis, not evolution. There's no transformation occurring. So the logical requirement for some similarity, but not too much, can be seen unmistakably in a widely used theory-laden term within phylogenetics, namely that a biological feature is or is not phylogenetically informative. Okay, what does that mean? Well, let's do a two-axis plot here. Similarity as a phenomenon on the vertical axis, evidence of transformation on the horizontal axis. And we'll put a scale of 0 to 100 on the vertical axis. 0 meaning there's no similarity between two or n entities. 100, total identity. They are exactly the same in every respect. So there's our metric on the vertical axis. And this is how it works. I'll just, let this run. Okay, so if we have no similarity between two entities, or n, two genes, two proteins, two invertebrate fossils, whatever, it doesn't really matter. The metric applies in all cases. If there's no similarity, we have no evidence of transformation. Okay, hold that in mind. Now watch what happens as similarity increases. As we go from no similarity towards higher and higher levels of similarity, we have increasing evidence of transformation, from relatively weak evidence to stronger evidence or higher degrees of evidence. And at some point along that slope, we will say, now these characters, these features are phylogenetically informative. Okay, now something very funny happens, funny as in odd or peculiar. As we're climbing that slope, we come to what I'm calling a zone of uncertainty. Why? Because when similarity reaches total identity, you go back down to no signal. of transformation. This is a paradox because as you are going up this slope, you come to this region here where you say, now these characters are phylogenetically informative. I have enough similarity that I can connect them in space and time, but not so much that I can't see change. What happens is as similarity goes towards identity and you hit this point, the signal of history drops to zero again. So it's zero here where there's no similarity. And when similarity is at its theoretical maximum of total identity, you again drop to zero. This is paradoxical. We see this when we go into the literature on the origin of viruses. So here's a figure from a paper by Koonin. And notice that you've got 6 major groups here arrayed around the periphery, the circumference of this figure. There is not a common ancestor here. You have, and this is an evolutionary diagram, you have a sort of pool of what he and his colleagues are calling non-viral replicators, but they do not share common ancestry. In fact, the caption of the figure, and I'm sorry that the StreamYard little box here is interfering with your ability to see that. I've never been able to see if I can just grab that and move it off. There we go. Whoops, go back. Oh, went back too far. I'm sorry, Subor. Just going to skip back here. I moved the box off so that people can read the caption. The caption in the paper by Koonin and colleagues is independent emergence of major groups of viruses. There's no common ancestry among these viral groups. Now, remember, a figure in a scientific paper is always a stand-in or a representative of an argument. So what's the argument behind this figure? What's the logic? Well, reflect on that a little bit. Why do Koonin and his colleagues argue for independent origins of these major viral groups? Well, here's why. Here's how they put it in the paper. A single common origin of viruses appears to be out of the question because viruses do not share a single universally conserved gene. Clearly, there has been no last universal virus ancestor. In other words, there is too much difference among viruses. The signal of similarity has dropped to zero at this point. So if you go back to our figure here, we're down in this corner, right? No similarity, no evidence of transformation. So we're down here in this portion of theoretical space. Another paper from Koonin featured this figure. And again, you'll notice that, and history is running here from past to present. So our evolutionary path is running this way along the vertical axis of the diagram. You'll notice that viruses are arising from I guess you could call it a pool of distinct ancestors, but those ancestors themselves are not converging to a common ancestor. They're simply present there in the virosphere without any shared ancestry here. So again, using the dictum, any figure is a representative of an argument. The argument that Koonin and colleagues are making is we can't find a common ancestor for all of these viruses. That's very significant. Another group, looking at the genetics now of viruses, point out that most of the content of the proteomes of viruses has no detectable homologs. In other words, when you go into the databases and look for the matching sequences, they're not there. And you can see that the overwhelming majority of the proteomes of these different viral groups is unique. It does not have shared sequences in the databases. So in their paper, they say these results indicate that orphans are a feature of viruses infecting all 3 domains of cellular life. Clearly, it's the majority of the genomes of these different groups, the presence of orphan genes rather than shared sequences. And they go on, orphans and virus-specific proteins overwhelmingly characterize viruses as gene creators. Now, one of the arguments about viral genomes that one finds offered to explain this pattern is, well, viruses are robbing genes from organismal groups. And the reason that we see these very high fractions of unique sequences of viral orphans is these genes have been borrowed from organismal groups that have gone extinct and so forth. They're not around anymore, so we're getting a misleading signal. These authors argue, by contrast, no, viruses are creating these genes. And that's why they're unique. That's why we find them only in viruses. Well, there is again a puzzle or a name being attached to a puzzle that, frankly, I find causally unsatisfactory. Viruses do not create genes. We find them with these high fractions of unique sequences, but gene creators, I think, is simply putting a label on a mystery. So if we go back to this diagram, this line will continue of unique sequences will continue to extend out into sequence space, and its implications for origins are unavoidable. All right, so I have shown this figure previously, and I have to apologize for it because sequence space, gene and protein sequence space, is high dimensional. It's very hard to represent in a 2D surface. And so this figure is the best I can do, because high dimensional spaces are, on a PowerPoint slide, are really hard to represent. There's a scientist I know who's quite gifted at visualization of biological data, and I hope to contact him because this is a problem that I'm going to have to solve for a project I'm working on, of finding a way to represent the high dimensionality of sequence space that's not misleading. In any case, with that apology in mind, what does it mean to say that viruses are gene creators? I don't think we know. What we actually know is when viral genomes are examined, they have very high fractions of unique sequences, meaning that the dimensions of sequence space on Earth go well beyond what is easy for us to comprehend. All right. Now let's segue to the origin of life. And my claim that, far from being separate questions, these two areas, the origin of life and evolution, are as closely connected as any two puzzles can be in science. All right. I first realized this a long time ago, almost 40 years. It was in a conversation with Niles Eldredge, who's a paleontologist, I believe still a curator at the American Museum of Natural History in New York, and one of the authors with Stephen Gould of the punctuated equilibria hypothesis. What was the occasion? Well, I was an undergraduate in the Honors College at the University of Pittsburgh studying evolutionary theory, and Pitt brought Eldredge to the campus to give some talks and to meet with students in the Honors College. And we went out to dinner one night, a small group of us. And Eldredge was asked about the evidential status, the standing of evolutionary theory. So this is circa 1983. I believe the conversation happened in 1983. And he's a very candid person. I've had a few occasions to interact with him one-on-one or in a small group. And he said, well, we've got a lot of the story in place. The story of the diversification of life and, the grand evolutionary narrative. But in a reflective moment, he said, what really, the really significant remaining puzzle is when we work our way back down the tree of life to its first origin, because so much is present there at that moment of biological importance, the ability to make copies of genes, to replicate the cellular state, to have the stable transmission of hereditary information from parent to offspring, of being able to diversify and distinguish yourself from other, or to make yourself as a species distinctive from other species and so forth. All of that, he said, is present there at the origin of life. That's what it means to be alive. And he said, and that's really still, an open mystery. What struck me in this exchange was Eldredge did not distinguish the origin of life from evolutionary theory itself. In other words, for him, it was a seamless narrative. You work your way back down the tree of life to the last universal common ancestor, and ultimately then to the origin of life. And the key events that make life, what it is, are actually present there at the origin of life. And really not so much later on, because, cells are operating. So it's this geometry. Now, I'm calling this the single theater scenario. Why? Because you have this bottleneck here at Luca, at the last universal common ancestor. Now, that bottleneck can follow from two things at least. One is that the initial chemical pathway from the prebiotic milieu to the first cells was very improbable. If that's the case, you will have, one lineage, one improbable lineage making it to Luca. And then Luca, by definition, is that our ultimate grandmother. You can think of her, give her a gender, let's say her, and all life diversifies from that point. Or those prebiotic pathways could have been very probable, in fact, perhaps even quasi-deterministic, right? With a probability approaching 1. They're bound to happen. Nonetheless, there will still be a cell, an entity that is the last universal common ancestor of all extant life, or all life for which we have any evidence. So there are two ways, at least, of arguing for there being a bottleneck, but it represents a point beyond which we cannot see, but from which all genetic and proteomic diversity must be derived. Now, what do orphans entail for that bottleneck? Well, they place an intolerable strain, theoretically, on that single theater scenario. And this has been emerging more and more from the work of people who think about the early history of life. So I've shown this slide previously. I highly recommend this paper to you in Trends in Microbiology. Only 2 pages. I like nice, short, well-written papers. And these investigators, Watson et al., say, look, when we examine the genomes of different groups, prokaryotic and eukaryotic, a glaring proportion of their gene families is simply not shared among most cellular lineages. And these non-shared families become more and more striking as you widen your lens, or you widen your scope of analysis. How and why, they say, is life massively reinventing its genes? It becomes a priority to explain the origin of genes without homologs outside a given lineage. And they say this must be done in a way or using models that are more complicated than divergence from a single last common ancestor. Now, Watson et al., these authors have, to my knowledge, zero sympathy for intelligent design. So I don't want to misrepresent them. They are doing their work entirely within the framework of naturalistic evolution. But as you'll see in a moment, there are implications that flow from this kind of signal towards design, even though these three authors themselves have, as far as I know, no sympathy for design. So Eric Baptiste, he's here, one of the authors of this paper, was a postdoc with W. Ford Doolittle at Dalhousie University in Canada. And Ford Doolittle himself has been an eloquent critic of the single tree geometry. In other words, all of life going back to Luca. Ford Doolittle doubts that Luca ever existed for a whole variety of reasons. But this figure is, I think, drawn by Doolittle himself. It shows a kind of mangrove type geometry for the history, the early history of life, going from the prebiotic world into the three major domains of bacteria, eukarya, and archaea. And you have this wild proliferation of interacting lineages here with multiple independent starting points. Notice what's missing is Luca. Luca is gone from the drawing. And again, to repeat myself, every scientific figure you see, every drawing, every visual representation is the companion or the representative of an argument. So the argument here is that when you look at the bacteria, eukarya, and archaea, and look at their genetics and work your way backwards, you do not, Ford Doolittle argues, you do not converge to a last universal common ancestor. So Baptiste was a postdoc with Doolittle, and they influenced each other, and published a series of papers arguing, look, Luca's probably not real. So what's missing is Luca. Now, Luca going away is not a minor event in terms of theory. It's not a minor event at all. In fact, I would, put it on a parallel politically or historically with storming the Bastille, the French Revolution. The old regime is on its way out, and the implications are everywhere. Now, let's take away my little filigrees that I had there and just think about these independent starting points. So there's probably more than 5, but 5 is plenty for the point that I'm going to make. Ford Doolittle does not draw these lineages converging to Luca because, as far as he's concerned, Luca actually didn't exist. So you have multiple independent starting points here crossing the threshold between the prebiotic world and the living state. Okay. I've shown this slide to a number of audiences, and a response that I typically get is, well, look, I mean, that's an easy move to make, right? The origin of life, it could happen more than once. But think about it this way. What if the origin of life even once was never going to happen? That is, via a undirected physical pathway. The origin of life via undirected physical process is not going to happen even once. Then it is certainly not going to happen more than once. So one of the consequences of getting rid of Luca and that bottleneck is one is in effect compelled to raise the probability of the origin of life as close to 1 as you can get it. Because if that probability stays near 0, what you are doing here is multiplying miracles, multiplying naturalistic miracles. So this kind of geometry, drawing it out, as Ford Doolittle has done here, compels Ford Doolittle and theorists like him to take that probability of the origin of life and move it along the wire between 0 and 1 towards 1. Get it as close to 1 as you can. But let's say it's close to 0. If it's close to zero, then it's not going to happen more than once. And the consequences are you find yourself being brought to the edge of a precipice. This one. The origin of life represents the crossing over point from evolution to design. You can think about it like a rope bridge. This looks like a very sturdy rope bridge. I'm not sure I would want to cross it. It's actually not a rope at all. Those are cables. But these people seem happy to go from one side of the chasm to the other. When you come to the origin of life and its probability, starting with undirected chemistry, you also come to a precipice that you are being invited to cross, I think, both scientifically and philosophically. I'm sorry for skipping that slide or skipping ahead to that slide. Before we get there, I want to make one point. In order to cross that bridge, you have to let go of something. You have to let go of a philosophical claim. And this is it. The rule of methodological naturalism, the statements of science must invoke only natural things and processes. So this is a point in your thinking when you're confronted with data that the philosophical framework within which you have been working sort of steps up to you and says, are you going to hold on to me or not? So I think the thing that one must let go of, that one must release, is this dictum about the practice of science, here enunciated by the National Academy in the late 90s. And you'll notice that this is an imperative, right? This verb, must, doesn't give you any options. And when you open your toolbox of explanation or your toolbox of possible causes, you see only natural things and processes. Here, this logical modifier has been added to drive the point home, where natural means deriving from physics. All right. So one final thought experiment, then we'll have some time for discussion with Subor. Think about it this way. Behind that door is a puzzle, some scientific puzzle, the origin of life, the origin of the animal body plans, the origin of consciousness, the origin of moral categories and Homo sapiens. Pick your favorite unsolved evolutionary puzzle. And I say to you, this is like a game show, I say you can have two boxes, one of two boxes. You have the choice between two. And box one, let's say, is one of the two. It has hundreds or thousands of solutions to puzzles, but they're all of a particular type. Let's call it type X. And I say that's one of your choices, or you can have box two. Now, box two has all the same type X solutions that box one does. In other words, at this point, these two boxes of possible causal solutions are exactly equivalent. If there's a type X solution in box one, you get it in box two as well. But the great thing about box two is you get the type Y solutions in addition. So let's say that the type X solutions are those that are based on physics. That is, in some way, they derive from what a naturalistic philosophy of explanation regards as the bottommost layer of reality. So physics is the bottom layer, chemistry rests on physics, biochemistry rests on chemistry, and so forth. And you climb up through the ontology of possible causes. But everything in this framework derives from physics. And let's say, for the sake of this thought experiment, that the type Y solutions are those that invoke a mind or an intelligence, where mind, intelligence, agency are in some very important sense not derivable or not reducible to physics. That's why they're distinctive. Okay, I've sketched this thought experiment from a number of audiences, and I've never been able to get anyone to take box one. Why? And this is the case even for audiences that have a lot of atheists and agnostics, right? Typically, what someone will say is, when they're confronted with this scenario, this thought experiment, well, I don't know if there are type Y causes, but it's possible that they exist, right? I mean, I may not have any evidence for them, but it's possible that they may exist. And given that bare possibility, that bare logical possibility, I want to at least allow for their existence. So, for the sake of of uh, explanatory power and comprehensiveness, I'll allow that they might exist. So I'll take box 2. Because no matter how you cut it, box 2 is going to be bigger than box 1. Now, apply this to something like the origin of life. If there is evidence in the origin of life that physics-based explanations are causally insufficient, you're going to want box 2. And you're going to want, therefore, to let go of methodological naturalism, which is this. That's methodological naturalism. And it is inherently limited with respect to explanatory options. Now, I think probably at its deepest level, the problem with this dictum, with methodological naturalism, is by turning everything over to physics, it renders invisible or destroys the possibility of agency, mind, or intelligence as real causes, right? They're gone. But notice what happens if we turn these arrows around, like so. All right. And we say agency, mind, and intelligence are causally primary, or put it this way, causally distinct. If they're irreducible to physics, then their efficacy will always exist independently of physics. And this way, we don't lose anything. We have all the explanatory options on the table. Now, even if I weren't a theist, I mean, I am a theist, right? That's one of the reasons I'm an intelligent design proponent. But even if I weren't a theist, this is the toolkit of explanation that I would want, where I've got all the options on the table. And I'm standing by my bridge. The origin of life confronts me with a precipice. I can sense that I want to cross that bridge. I have to let go of methodological naturalism, which never should be identified with science. If science is an open-ended pursuit of the truth, methodological naturalism hinders that search because it eliminates from consideration the possibility of causes that may be real and that may have made a difference in biology to the history of life as we see it. So even if I weren't a theist, I would want this as my causal toolkit, because I want the world to be as interesting and surprising as it actually is. And I think that's my last slide. So now Subor and I can have some conversation.
Brilliant. Thank you so much, Paul, for that presentation. As you were speaking, there was one burning question in my head. This was going back to the example you gave of Lucca and it being the akin to, the storming of Bastille. Something came to my mind, which is, could we say that this revelation, and I think it is a revelation because, we both have the belief that there's God's world is a type of revelation, right? The challenge to gradualism that Eldridge and Gould and others put forth, that was a real stab at the heart of Darwinism, and it still hasn't gone away, as Myers and others have pointed out. But would you say that this challenge to Lucca is not just evidential, but it's theoretical, so it's stronger, and it's maybe perhaps a deeper stab than that of gradualism? Because with gradualism, at least they try and come up with some sort of answers, but here it just seems like, the emperor has no clothes.
I do think that Lucca, for a whole variety of reasons, sits right at the center of evolutionary theory. And jettisoning Lucca, getting rid of Lucca is not a minor move, because so much is contingent theoretically on its existence. And in work that I'm doing over the next year, I'm looking at evolutionary theory with Luca and without Luca. And the two forms of the theory end up having very different consequences for things like assessing similarity, assessing homology, building phylogenies, right? You're no longer converging towards a singularity, but all of these lineages have to have histories. And a single tree topology or history is strikingly different in deep ways from a forest of trees. And so the consequences ramify. When you get rid of Luca, the consequences ramify through theoretical biology, as I've said in previous live streams, in a way that's very hard to stop. When you cut down a tree at its base, the whole tree comes down. You're not just trimming a few branches here and there. The whole tree comes down, and you're looking at a very different situation. So, yes, bottom line, having Luca go away has just all kinds of consequences, some of which I think we haven't even really grasped yet.
Yeah, I think so. I think that's a good way of putting it. And something else that came to mind when you were speaking is we forget sometimes not only the bigger picture, but the bigger picture, which is how do we understand biological evolution without chemical evolution? Because a lot of the times the popular sort of rhetoric you hear is no, Darwin dealt with this particular thing, the origin of life is a separate question. And you've shown, and others who are definitely not intelligent design proponents also recognize, actually you just simply cannot break these two. You have to make fundamental assumptions about one which impacts the other downstream all the way. So do you think that this is this is a point in history in which we're going to have philosophers of science looking at these questions from a much more deeper level now? Because now we have evidence to show, we have empirical evidence to show that actually once you make certain assumptions and then you go out and look for that particular data, you will find things from which you will have to go back to your initial assumptions, because those assumptions being tweaked completely change the data. It's like a paradigm shift. It's like a gestalt shift. The old
yes,
the pictures that we used to get back in the days of the old lady, or is it a duck or rabbit, or that kind of thing.
Yes, no, I think you're exactly right. That there is this. I guess you could call it a conversation or a dialogue between assumptions and data. And changing one's assumptions changes how you evaluate data, and then you cycle back and look at your assumptions again. And I think that this kind of philosophical commentary has already commenced. I've interacted over the past decade with Joel Velasco, who's a philosopher of biology at Texas Tech. I think he's still there on the faculty. And I've watched in his work, and he's definitely a philosophical naturalist. He is not an intelligent design advocate, but he's looking at what happens to biological explanation as you change your views on the tree of life. And I reckon I'll try to include some references when I send them to some of his more interesting recent papers. There are downstream consequences, and what you assume, what you take to be the case, let's say, for the origin of cellular features like the ribosome, will have a direct bearing on how you construct or deconstruct the tree of life. So I think the case that one can make for the distinct nature of what was the origin of life and what is the history of life, yes, those are different questions. But if you think seriously about either of them, you find that, as I said in a previous session, they interfinger at every point. And I like people who are honest and straightforward about the problems of their theory. I try to be that way myself with intelligent design. I would encourage evolutionary biologists, be candid with each other, be candid with your students, be candid with the public about the fact that the origin of life and the history of life, once life begins, those questions go like this. They
Brilliant.
connect in a deep way.
Absolutely. Absolutely. So now let's move on to why you're going to be going on a break for about a year. So you have a publication coming out, God willing. This publication is going to be a very much needed um, academic resource on universal common ancestry, right?
Right.
So we could think of it like a lot of these live streams are just precursors to a much deeper insight that you want to give. So the first question I want to ask you is, who is the audience for this book?
So this is a challenge because I'm trying to write a book that has at least two overlapping audiences where the region of overlap is not very great. So lay readers, the general public, and professional biologists and philosophers of science. So I want my family members to be able to read and enjoy the book. By family, I mean my extended family, because actually my immediate family, my wife's a doctor, and both of my daughters are in the sciences. So I'm expecting to put them more on the expert side. But cousins of mine or people that I meet in my daily life, I want the book to be compelling to them and readable. I also, though, want to reach professional biologists. So there is a tiny region of overlap in the Venn diagram between those two audiences, and that's what I'm aiming for. And my model of sort of nonfiction writer is Michael Lewis, one of my favorite nonfiction authors. He wrote The Big Short and Moneyball and a whole range of very compelling nonfiction books that read like novels, right? You can't put them down. And the challenge for me is I'm dealing in many cases with very technical material. So I'm not underestimating the difficulty of hitting my target audience.
Yeah. I mean, Noble comes to mind. He has a very unique ability to take very complex ideas and simplify them. Perhaps this is due to his love of fiction. He gives the example of the difference between the gene-centered perspective and the holistic perspective, using a robot which sees the difference between itself and another human,
Yeah.
being Brownian motion, being the random number generator, right? Like, just very interesting ideas like this. It takes a lot of brain juice, it really does, because I'm sure you spend a lot of your time just trying to think. I mean, even these live streams, you've simplified a lot of very complicated ideas. So I guess that's the real challenge, isn't it?
It is. And I'm glad you mentioned Dennis Noble, because he's another example of what I would like to do. I remember a few years ago reading this wonderful short book he wrote called The Music of Life.
Oh, yeah.
And just a beautiful piece of writing. And getting really for the first time a comprehensive view of the organism first perspective on living things.
Yeah.
Where he said, I'm going to contrast my position with that of my former student, Richard Dawkins, and show you why, even though genes, DNA is essential, it is not a privileged causal level in
Yes.
understanding biology. Frankly, Dawkins himself, uh, The Blind Watchmaker is just a masterfully written book, taking difficult concepts and making them intelligible to lay readers. In fact, when I taught writing at the University of Chicago as a graduate student, I worked in their professional writing program. I would use Dawkins' chapter on bat sonar
Oh
because
yeah.
it's just so beautiful. So I've got plenty of models of good writers to emulate. And, to describe the book itself, it comes in 4 major sections,
Mhm.
15 chapters total. These will be long chapters with a variety of appendices where I can place more technical material, get it out of the way of the story, but it's there if you want to consult it. And I also hope to have a companion website where if the reader wants to, he or she can go into much greater depth, on some of the more technical questions. And this will be a unique feature of the website where there will be a whole range of thought experiments that people can try. So the book itself will have several extended thought experiments, but the problem with thought experiments is they can get shop worn. In other words, people will hear about them like, oh yeah, I know the answer to that one. And a thought experiment fails if you already know the answer. So I'm going to set up a companion website where if you've already heard about the thought experiments in the book, I tell you right there in the preface of the book, if you've heard about these ones, go on the website because I'll put new ones there daily or weekly where you don't know the answer. So you won't be able to cheat, in other words. It's going to be, again, I don't underestimate the difficulty, particularly with professional biologists, academic biologists, for whom universal common descent is part of the furniture of reality.
Yeah.
And they frankly find it offensive, bothersome, worrisome that someone would write a book critiquing this theory. It would be like asking an astronomer, does the Earth go around the sun or the sun go around the Earth, right? You're just not going to entertain that second idea. So getting people to actually read the book, I think, is going to be a feat.
Yeah. I mean, it's kind of like going back to the 19th century and trying to get physicists to see, electromagnetic waves without the idea of the luminiferous ether, right? It's just
Right.
there's no medium. It's like it's such a deeply ingrained idea that you can almost imagine it's like Darwin trying to challenge design. It's him versus everybody, because one of the things which I think we can sort of concede, because people like Philip Kitcher have conceded this, that design was very fruitful, even though he believed it to be wrong in physics, right? So we can say, well, we can see the efficacy of having universal common ancestry there, leading to some sort of you need some sort of background assumption, even if the assumption is wrong, in order for you to function, right? So sometimes it happens, and I think this is a subtle point which I was listening to Signature in the Cell again this morning. It's just such a brilliant book, and one of the brilliant points that came up is sometimes intelligent design proponents and Darwinists are making the exact same predictions, yet the intelligent design proponents aren't allowed to use the same data to explain how that fits within their paradigm. And it's almost as if it's exclusively to be explained by the Darwinian perspective. And the same thing applies with universal common ancestry, that, people can say, well, UCA allowed us to see this. Well, so would have separate ancestry. But this subtle point is not granted often.
I'm glad you mentioned that, because one of the things I'll do in the book, in fact, in the second chapter, is explain to the reader this is a powerful and elegant theory. It has many features that are philosophically commendable.
Yeah.
In fact, I end the first chapter by saying, I want to convince you that I should not have written this book. And the title of the second chapter is the loveliest theory you could ever want to see. So I want to tell the reader the reason this theory is so central is because it performs all kinds of important theoretical functions for biologists.
Yeah.
You know, and in other words, it's like, I want the reader to understand. I appreciate the power and elegance of this theory. Where do I have a problem? It might not be true.
Yeah.
The Ptolemaic geometry of the universe was elegant, and it was consonant with our daily experience. Right? You get up and here comes the sun, and you see. If you stay up at night in the ancient world, you see the heavens rotating around you. In any case, I hope that the book will be done and available in bookstores a little later than this time next year. So late summer, early fall of 2024.
Yeah.
I have an aggressive schedule for completion. The big challenge I face at the moment, or one of the big challenges, I've mentioned a few, is picking the right examples to include. But I hope that the story builds from part 1 to part 4. And my last chapter is entitled Wide Horizons, where I suggest to the reader that letting go of the centrality of universal common descent is frightening. It's scary because you're letting go, for academic biologists, of the organizing theory for all of biology. But here are some things that follow from that you may find sufficiently attractive that you're willing to let go and see what might be the case down the road. So anyway, something to look forward to for next year. And I'm very excited. The chapters are coming together quite nicely. And, we will reconvene, Subor, you and I.
Absolutely. I mean, I'm going to miss you. I'll put it that way. And so will the viewers. And I would love to just hold the book up next year and, go up to my local Darwinist and say, look, Paul's book is going to prove to you that Darwinism has everything going for it but the evidence. Paul, it was great having you on the channel. We're going to see you next year, and I'll keep the viewers updated on the YouTube community tab on this channel, my communication with Paul, with his permission, any updates regarding the book, any drafts which are ready. I will keep the viewers updated. I'm sure a lot of people are going to be waiting. So any last message from you, Paul, before we end?
Just if you are a person who prays, pray that I'll get this done on the schedule that I've set for myself. I've got a lot of writing to do, a lot of organization, and I'll be honest, I believe in the power of prayer. So
yeah, absolutely.
I covet that support.
Brilliant. So thank you so much, Paul, for your time. We hope and pray that this book comes out in time, and it's going to be lovely. I'm really looking forward to it. So until next time, everybody, assalamu alaikum wa rahmatullahi wa barakatuh.